Hello. Today I would like to talk about matching networks. Currently I'm learning about RF circuits, and I had a really hard time understanding some of the intuition that's used to teach matching networks. And I was hoping I could share what I've learned, my perspective, and maybe help some other people if they're struggling with it. Because Lord knows I very much struggled with this. And also, I'd say before watching my video, it's great to watch some other videos out there too that really explain why and experimentally show how this how matching networks help solve this problem that we have. So yeah, and I'll link some of those in the video description too. And great to see those before this. So anyway, matching networks. What's the problem? Our problem is that we have our modulated signal that we want to amplify, and then we want to transmit it through some antenna, some load connected to the amplifier. And we'll say that our amplifier has an output resistance of 25 ohms. And we'll say that our antenna has an output impedance of 50 ohms. Now, the 25 ohms and the 50 ohms, they don't match, and that's not good. We want their impedances to be perfect so that our output right here is going to be a perfect ratio between the two. So what we need to do here is we need to somehow magically, through the magic of impedances, reduce this 50 ohm antenna to a 25 ohm antenna. Make the real part of its impedance equal to 25 ohm. That's what we need to do. Magic. And we want this to work. I'm following a given problem in the textbook, RF microelectronics. We want this to work at 5 gigahertz. So what we do, the solution to this problem is insert a matching network right here. This impedance here. And the actual matching network in this case to reduce this resistance, let's say we have this, our antenna is like a resistance. We add an inductor in series and then a capacitor in parallel. That's what you do to solve this problem. And we'll go into the math of how we do this, but we'll also go into like one of the things that all the textbooks that I've read that try to explain this, they go about this explanation of how to think about this. The resistance here, how it cuts the resistance in half, and it is very hard to understand for me. I had very, very hard time grasping this intuitively, and it's this idea that you can look at a series or it's called series to parallel conversion or parallel to series conversions. And what that is you take a resistor and a capacitor in series like this, and you say that under a given circumstance of a given frequency range, it's the same. It behaves the same in our circuit as a resistor and a capacitor in parallel. And I went here and proved it with math. Made sure I was correct. Didn't just follow the textbook. I literally wrote this out and had a lot of trouble doing that. I'm not the greatest at math. And we went and solved here for the impedance here and the impedance here. And what we want to do is we want to set these equal to each other to prove that they do behave the same. And we go ahead and do that. We have our impedance for the series part, which is this, CSRS times S plus 1 over CS times S. And our impedance for the parallel, which is resistance parallel over 1 plus CPRP times S. We set them equal to each other. And we get we get an equation for them being equal to each other. And with just one equation, that's not enough. Oh, I lost a piece of paper. With one equation, that's not enough. We want to set both the imaginary and the real parts to 1, and that gives us 2 equations. This equation and this equation right here. And what we do is we go ahead and we solve for the resistance in parallel and the capacitance in parallel. And when we do that, we get, for the resistance in parallel, we get the resistance in series multiplied by the 1 plus 1 over Rs squared CS squared omega squared. And this 1 over RS squared CS squared omega squared, we're going to rename this the quality factor for this parallel configuration of a series and a capacitor. And we're going to say that a resistance in parallel is equal to the resistance in series times 1 plus the quality factor squared for parallel. This is what it's telling us, is that if we choose to look at this circuit, if we choose to look at this circuit in series as if it were in parallel, it's going to change that resistance, the real value of the impedance, to this 1 plus the quality factor squared. So it's going to, the real part of our impedance is going to increase by a factor of 1 plus Q squared. Okay, and we have our value for CP as well, and we'll see that this doesn't matter as much as it does for the resistance. And what I mean by that is, if we assume that this quality factor squared is much larger than 1, which turns out to be valid for a lot of conditions, we can ignore the 1, and we can make this assumption that taking a resistance in series and changing the way we look at it to see it in parallel, the value of the resistor in parallel is going to be equal to the quality factor squared times the resistance in series. And our capacitor, seen in parallel, is going to be roughly equivalent to the capacitor seen in series. Now this is the cool part, and because right here we're talking about the imaginary part in the real part. The real part is going to change. Okay, this is what we want. We want to, like, yes. So now if we go the other way and we want to go from a take our capacitor and resistor that we have in parallel and consider it as if it were in series, we would go the other way. We would say our resistor in series would be the resistance in parallel divided by Q squared. So we're reducing our resistance when we look at it in series. So a little bit more, going back to like our original problem, why does that help us? We were saying here, ignore that. We were saying here that we want our load resistance to not be 50 ohms, we want it to be 25 ohms. And if we add in this capacitor and look at it this way, this part in parallel, if we consider it as if it were in series, that the resistance, the real part of the impedance, is going to be reduced. Okay? So if we go ahead and actually solve this parallel part, because this is the actual circuit, we're not actually putting the inductor and the capacitor and the resistor in series. We're not actually doing that. That wouldn't give us the correct configuration. That's not right. That's not what I was talking about. I made that, I was confused. I thought maybe you actually put the inductor and the capacitor in series. No. We just look at it and consider it as if it were in series. And that's where here we solve this part for the impedance and get this equation. And we want to take the real and the imaginary parts. And to do that, we have to multiply by its complex conjugate to get the imaginary part out of the denominator. And that gives us this nasty looking thing. And if we take the real part of this nasty looking thing and simplify it, we get the real part is equal to 1 over RL times C squared omega squared. And this is the part that we want to equal 25 ohms. We know that our actual resistor right here, we know that it's actually 50 ohms because we can't change it. It's the antenna's impedance, the load resistance, right? But we want the real part to look like it's 25 ohms. And that's what this is saying right here, is that if we, choose a value for C1 correctly, we can make it the real part of it look like 25 ohms. And that actual value, given at 5 gigahertz, the actual value turns out to be 0.9 picofarads. If you go and actually solve it, it's in the textbook. And that brings us back to why we had the inductor here. If we just had the capacitor, it'd be we would augment the real part, but then we would have a change in the phase. We would change the imaginary part of our impedance, and that's not what we want. So what we have to do is we have to take the imaginary part of this impedance here and set it to 0. Okay? And when we set it to 0, we can then solve for what value the inductor needs to be to bring it back to 0, given that we have this capacitor of 0.9 picofarads. Because the capacitor being added there is going to change the phase in the minus pi/2 direction, and an inductor is going to change the phase back to the pi/2 direction. So we picked the right inductor that makes it 0, right? And that turns out to be 1.1 nanohenries. Okay? That's the whole idea here. Now we have those values. Here's more math. I actually did it. I did the math. Now that we have those values and we take an inductor of 1.1 nanohenries and 0.9 picofarads, we get the real value of our load, our antenna, to be 25 ohms, which matches the resistance of our the output resistance of our amplifier, and that will give us the perfect power distribution, power transmittance to the antenna, and it solves this issue. So I hope that made sense. The main thing I wanted to say here is that it was very confusing. This whole parallel to series conversion, the explanation was very confusing to me, because we're not actually making a circuit that looks like this. We're doing this. We're doing the capacitor in parallel with a resistor, and adding an inductor. Like, it's just a way of seeing it so that you can say that we're adding them together, sort of adding them in series. It's just a way that I think in the textbooks they're using it to try to intuitively explain it to you without, for me, I was just really hard to grasp. Like, you're giving an explanation to a phenomenon with an intuition that you can look at it this way. That's basically what it is. And honestly, that doesn't make much sense to me. It makes much better sense to me to just look at it as this and see that we're augmenting the real part and canceling out the imaginary part. So we're, reducing the impedance seen from the amplifier by our antenna or our resistance of the load. That makes much more sense. That was easier for me to understand it that way. But I do see where they're coming from with trying to say you can convert the circuit. You can say that the circuits are the same because they behave the same. And yeah, that's the whole thing. So I guess don't lose hope. And take whatever explanation works best for you, because all this stuff, it really is it's just about how you understand it. And if you understand it, that's good enough. So good luck to all the other people out there studying, and thanks for watching.